lubrication, instant spool performance. We'll do part 2 already, at least film it, for the turbine wheel. We're going to get into turbine housings on this one. But I told you guys I'd tell you about the 3 things the turbo cares about, and then I'll also tell you what exhaust manifolds do, especially in limited charger, or as far as a class rule goes, or limited charger, as far as there's nothing available and you don't want to change the charger out, but you know what you can do in certain part, and by doing this you can get more out of your turbocharger, possibly, as long as you can verify it's a turbine issue and not a compressor deal, or if you're trying to move the peak locations to a higher RPM. So the horsepower is the same. Say if it makes 800 horsepower at 3600 and you want to make 800 horsepower at 4000, it'll drop the torque number down because we're making the same horsepower at a higher RPM, but we can make that horsepower at the high RPM without us running into, say, EGT issues or engine VE issues, volumetric efficiency. So the motor's still going to stay happy and be producing that horsepower just at a higher RPM. So in case you need more wheel speed, more track speed to the track, you want more wheel speed going down a bull track, these things apply. So turbine housings. Guess we should go over the 3 things the turbo cares about. Number 1 is going to be, or the 3 things, is heat, pressure, and velocity. Here's the catch-22. The velocity matters up to the point where the turbocharger is rotating at its maximum, basically like its maximum rotor speed. Like any more, say you're operating right at the choke condition, at this choke condition, so everything up to the choke flow point, usually this is where peak torque is going to be on most turbochargers. We're using all 3. So heat energy, pressure energy, so your drive pressure, and then the velocity. So as far as the exhaust speed goes, that's going to be based off of the size of the manifold, the size of the exhaust valve, the exhaust port, the piston speed as far as when the exhaust valve opens, as well as the RPM. That's how all those things are going to be working. Once you get to the point where you're past peak torque, the only thing at this point now maintaining the speed of the turbocharger is going to be heat and pressure. The velocity, because the velocity through the throat has now hit the point where it's not going to accelerate anymore. Now the turbine wheel is only extracting heat and pressure. So the pressure is creating a velocity through the nozzle, but it's not a rapidly increasing pressure that we would say is velocity or a force. You know, if the gas has some good speed in it and hammers into the turbine's inducer, that would be velocity. Now if we're doing a constant push against the turbine wheel, I like to see that as pressure. So heat, the best way to, heat's helpful, but heat's not everything. It's a very small thing. And then an easy way to make this make sense is to have an EGT probe before the turbo wheel, EGT probe post turbo wheel. And everybody says don't put the EGT probe past the turbo wheel. If you do put it past the turbo wheel, add 300 degrees or add 400 degrees. This is based off of typically 1200 degrees with the drop across that. It would then be 800 degrees, 900 degrees. So you can see, say we used 1000 degrees and post turbine wheel is 700 degrees. Out of that heat energy, there's still quite a bit of heat left in the exhaust gas. So the turbine wheel, although it does care about the heat, it's not as important as the pressure and the velocity, and then mainly the pressure. So don't get too caught up on the heat. Yes, the turbo blanket will help. Any change in the heat is going to show a change in the turbine wheel. Increasing the gas temperature is going to allow it to travel at a greater rate of speed easier. So doing anything like that certainly helps. Higher EGTs, and as far as tractor pulling goes, we usually shoot for around 1500 degrees on the EGT gauge. That heat helps maintain better flow through the turbine housing because the speed of sound is higher. And as well, it tells us that we have a hotter event in the chamber, given the time is not too low and all that stuff. We want the chamber to be fairly warm, so our timing events, as far as when the initial event happens, is where we want it to be. So too low EGT with a lot of fuel can cause us to have low ignition timing, even though we're putting the fuel in early. The quantity we're putting in has a high probability of taking too long to absorb that heat and get lit off. So our power strokes happening too late, or as the pressure event during the power strokes happening too late in the event, and the piston's running away faster than the burn speed of the event itself. So what housings do, hopefully visible, how we can do this is we have, say, a baseline, and we're going to have this slide, and then this slide. So we can stay, since we're all used to these sizes, because even Borg Warner, well, not Borg Warner themselves, but we've classified them as this, a 0.70 and a 0.80, a 12 and a 14, so we can go 12 cm, we can go, hopefully I'm close enough, 18 C. So depending on the size of the motor, every time an exhaust valve opens, we have a spike, so a pulse wave. It's going to look like this. Every time an exhaust valve opens, you have a spike. Now this pulse only matters actually up to a certain RPM, and that RPM is going to, it's frequency based. And so that RPM is going to be based on how many cylinders there are and what size each cylinder is, and how often they're going off. So, but to keep this easy, on our 6-cylinder 5.9 liter motors, it comes out to about 3,000 RPM. So everything from 0 to 300, 0 being the most prominent pulse, and at 3,000 RPMs, you would have a pressure number, but the line's going to be fairly flat once we get to 3,000. So 1,000 RPMs, you're going to have here, and then 1,200 RPMs here, and 3,000 RPMs. It's just going to sit basically flat in these motors. So that's why on a lot of these high RPM trucks, you don't see, a lot of them have like a divided manifold on, because that's how they come. You know, nobody really makes an undivided performance manifold. But when operating above 3,000, you'll see that they'll have spacers off the exhaust manifold. So we can see here, this spacer that's coming off the manifold. It's still may be divided, but the housing that's on this massive HX82 in this triple turbo setup, 2 atmospherics, 1 manifold, not going to be a divided housing, nor does it matter if it's a divided housing. These motors operate at very high engine speeds. They're not looking for response time or spool up characteristics in these motors. They will get plenty of speed out of the rotor just by getting the engine's RPM way up high. This truck here is known as Climate Change. It is a mechanically injected inline injection pump truck that competes in the index racing against like Firepunk and those guys. ODSS racing, there we go, series. It has 6 runners into 1 pipe, so a log manifold. That log manifold then feeds a single tube all the way into the passenger compartment where the first stage turbo is located. That turbo, the exhaust goes through that first stage and then goes all the way back to behind the truck into the bed to feed the other 2 turbos that are located in the bed. So like I said, in this case, they don't need any kind of divided pulse tuning stuff going on, and it wouldn't matter anyways if they were trying to play with that. So there's a lot of setups out there you can look at that are all set up like similar to this in racing and sled pulling. and stuff like this that's going to cause mixing of the pulses. And in these applications where they're going to be running 5,000 RPMs, 4,000, 5,000, 6,000 RPMs, it doesn't matter. There's no difference. They're not worried about spool up. They're getting things up to 4,000, 5,000 on the line and then taking off. If we increase the displacement of the motor, the pulse goes up. So as long as this pulse, when operating in this area, or pressure signal, stays below what the housing is rated for, peak torque and EGTs and all that stuff will stay good. As the power level goes up, the pulse gets bigger. The engine's dynamic displacement is going up. What will happen, say we went from a 5.9 to a 6.7 motor on the same housing, the pulse can go past this. So what happens when the pulse goes past the line is we'll see a spike in drive pressure that isn't doing any kind of usable work. So any pulse amplitude or gas pressure below the housing's designed line will be turned into useful work on the turbine wheel. When it exceeds the line, this amount of pressure and signal energy past what the housing is rated for just turns into drive pressure that will be consumed by the housing once the housing has done what it needs to do with everything that was below it. If you want to see how this applies, you can look at semi-truck engines that have low flywheel horsepower. So we can look at a lot of the older semi-truck motors, 855 cubic inch motors. They'll have a fairly small compressor wheel usually, at a 335 crank horsepower, 855 cubic inch diesel motor. They'll have a very large turbine wheel and turbine housing, and the reason for this is that 359 cubic inches at 2,000 RPMs only needs 12 centimeter. Let's take this up to a 32. When you get to 855 cubic inches at 2,000 RPMs, that cylinder is much larger and the exhaust event is much larger. So that signal event goes right up like so. So the larger housing is there for the larger displacement motor. The compressor wheel can stay fairly small. A lot of these 335 flywheel horsepower motors have anywhere from a 65 to a 70 something, 73 millimeter compressor wheel. And the main reason that the compressor wheel got larger is because from an OEM perspective, that compressor wheel has to say theoretically run 100% duty cycle for 4 hours or 5 hours. So for longevity reasons and turbo speed reasons, they'll make the compressor bigger to bring it back to a slower rotor speed. So as far as wear and tear on the turbocharger itself, it stays in very good shape. But when the exhaust gas, we'll probably go to the table next, so it's kind of showing pulses. So if you go to a 2-liter motor at high RPMs or whatever, a 2-liter engine, it has smaller pulses. So a 2-liter motor producing, I know this kind of goes a little bit against it, but a 2-liter, they do, it's not set in stone. I guess let's put it this way. A 5.9 liter on one of our turbochargers, our max effort stuff will do about 930 to 940 wheel. And with that same turbocharger on a 6.7 liter motor will do about 840 wheel. So the increased displacement does cause the turbine housing to go inefficient sooner, as it can't keep up with what the displacement's doing per cylinder. So the same thing goes for as the motor gets smaller, the same size turbine housing typically can eke out a little more power. So if we went from 5.9 to 3.9, then that housing's now good for a little more horsepower. Not a big change, but certainly it is capable of supporting a little bit more. And that's all given that the compressor can keep up with that. So it's not like I think I said it earlier where it sounded pretty set in stone, where the motor's dynamic displacement goes up, which is occurring, and it does matter, but there is some wiggle room in there as far as a smaller displacement motor can take more advantage of a smaller housing than that same housing on a larger displacement engine.